You guys saw the midterms up. You guys want to see the averages or something, or you can see it already? I don't know how to. Okay. Okay. I guess I had it up. Let's see whether I had it up. Okay, I guess that's it. Okay, so. What is this? Okay, so this, I guess I can't show you that, but the average is around 80, and that's the distribution of the scores. I have to log in, and I don't know whether I have internet connection. Okay, so the way you do this is you go online. You should know how to do this, right? -S MT1. Okay? If you do that, yeah, they're up. Yeah, so they're up, and you'll get them back in a section. Okay, so is that something you can do? And that's what it looks like. So there's a few guys who did a few curve killers here. So please be kind to them. Don't track them down. And okay. And where's ocular? Oh, that's not it. Okay. Okay. Okay, so this is the part of the semester where everybody seems to be sleeping in lecture and stuff like that because I guess projects are due or projects due this time of year. Who has projects due? Yeah. Okay, so I don't know. Any questions or concerns you want to bring up here, or? Okay, so I can go on with the lecture. Is this too loud? It seems to be reverbing here. It's not reverbing. Okay, so yeah, nobody's here. Okay, so we're going to talk about greedy algorithm today. All right, here I'll tell you a story to settle you down a little bit. Okay, because okay, so this is it's the middle of the semester. There's a lot of projects, so I'm going to tell you a long story about my childhood. Okay, so when I was a boy, it's about an algorithm. So you can have a story about an algorithm from when I'm a boy or about computer history. What do you want? Okay, so I'll do the other one later maybe. Have you seen Forrest Gump? Okay, so it's sort of I have a Forrest Gump moment, but I'll do that later. So there's this algorithm. Like if you have a school and you have kids who go to the school and you have a bus and the school's in town and there's a lot of people who live out of town. So to minimize the time that people are on the bus, what you should do is you should pick up everybody out of town, pick up everybody in town, and then drop them off at the school. And do the reverse on the other way, right? You drop off everybody in town, and you drop off everybody out of town, right? This is sort of the minimize the time on the bus for the students, right? So it's sort of, but what's wrong with this algorithm? Well, the poor kids out of town, they're sitting on the bus the whole time and having to wait for the guys in town to be picked up and to be dropped off. So they have to get on the bus earlier and be dropped off later. So they pay. Every time, every day. So I lived in a small town in Texas, and they did this. This was the algorithm. I lived in town, and there's all these people who lived out of town, and it was a small town in East Texas. It was sort of a small town in East Texas. So you can guess what the ethnic mix was, right? It was all white in town, and it was all African American out of town. So it was like just, it's sort of typical for the South in that time, and probably, I don't know, maybe now. But somebody gets the right idea, okay, well, this isn't fair, right? These people out of town are having to be on the bus extra in order to stop and pick up everybody in town and stop and drop off everybody in town. So they reversed it. so they reversed it, and you go out of town, you're like, wow, this is where I live, right? 'Cause you never see these places when you live in town, and so then they start dropping off these kids who are quite a bit poorer than the people who live in town, and in fact, they lived in houses that were appalling, and of course, what do the other kids do? They make fun of them. Oh, so look where Bobby Joe lives. Ah ha ha. And this guy's sort of a badass dude at school is no longer so. So I don't know. Algorithms are complicated. So that lasted a week, and then we went back to the old way. So it's always complicated to optimize, right? You don't know what you're doing always in the real world. In this world where we have these problems, they're given to you, in a clean fashion, but life is not always so clean. Okay, so all right, so this is the outline of what we're doing. This is the greedy algorithm. We're going to optimize a bunch of things where we're given this input in a nice and clean fashion, and we know what we're doing. So let's see how to do this. Okay, so one thing we want to do is compress. This is a very generic computer science thing to do. Right? So there's 16. So we know how to do this. If you have 16 characters in your alphabet, how many bits do you need to represent it? Well, it tells you. But you should think it through, right? Why that's true, right? You need 4 bits, because with 4 bits you have 16-bit patterns, and you can just write down for A, all zeros, for B, all zeros with 1 1 at the end, and so on. You count to 16, count to 15. Okay? So this is the standard thing. So just to get oriented, this is what we're starting with. This is what we get. Like if we have 16 characters and we have n characters in our file, we have 4 times n bits. Okay? Is that clear? Is that something? Okay. So okay. So one idea is in English, for example, the vowels are more common. Right? Does everybody know that? Right? It makes sense, right? Some of the vowels are more common. And so maybe you want to use a shorter representation for the vowels than you do for other characters. Does that seem like it might help? Right? If half your file is A's, you should use maybe a shorter representation for A and longer representation for everything else. Okay? Okay, so let me show you an example of this. Okay, it's called Morse code. So this is Morse code, another thing from even before my childhood. The symbol for E was dot. Okay, so do you ever see those old movies where they're doing this thing on the dot, 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 dash, 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 dot, dot, dot? What did I just say? Oh, yeah, dot, 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 dash, 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 dot, dot, dot. What did I say? SOS, yeah. So, okay, this is something they do if you're in trouble. So and E is clearly shorter because E is more common. Okay, so these, I guess they're less common. Okay, so there is an encoding, and people have done this for a long time, using shorter representations for more frequent characters. So the common characters are shorter. Cool, that's cool, right? Isn't that cool? Okay, so, and it's nice for us as computer scientists, because now we can think of a dot as a 0 or a 0 and a dash as a 1, right? Another story for my youth is my physics major friend. I would say, aha, everybody did everything in physics 50 years ago. What are you bothering with? And we were really very kind to each other and supportive. And he would just say 0, 1, 0, 1, 0, 1 at me. Okay, so we're happy when that happens. I'm like, all good with 0, 1, right? This is good for computer scientists, right? Because we have dots and dashes of the zeros and 1s. Okay, so, okay, now what is this encoding? What is this thing? It's dot, dot, right? So what is it? Here's a little problem with Morse code. It doesn't quite work for us, right? We can't just translate Morse code into zeros and ones and have it work for us. Right? So it's either I, right, which is a dot dot, or it's, sorry, somehow it's not working very well. Okay, so or EE. Okay? Does that make sense? So what's the problem here? Yeah. Yeah, there is a way. I mean, and that's how they do it there. They pause. They do dot, 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 and then they pause. Dash, dash, dash. Dot, dot, dot. Right? But we don't really have a pause in the computer. We just have our zeros and ones. Right? So there's a problem here. We can put separators in, but then the separator is going to cost us something, right? We have 4n bits. What are we going to, now we have to represent a separator again. And then, it's sort of unclear how to do it. When each set of bits, each 4 characters corresponds to, each 4 bits corresponds to a character, the translation from the file to the characters is obvious, right? You take 4, take the next 4. But now if you let them be variable length, like Morse code, there's a problem. And one has to understand how to deal with that and still maintain some efficiency. Okay? So for binary, we don't have this third character. And if we did, we would want to use it more efficiently than just a pause. For people, that's fine, right? Because people are weird. We don't even like people, so it's okay. But for us, we want to do this in binary, right? They have this other mode of operation, pause, right? Which is perfectly efficient for a person, but not for a computer. Okay, so the idea that we're going to use is no code word. So for each character, we're writing down a code word, right? For A, it may be all zeros. For B, it may be 3 zeros and a 1. So for each one of those code words, one should not be the prefix of another. That was the problem with the I and the EE. The code word for I was dot, or the code word for E was dot, and the code word for I was dot dot. So the code word for E is a prefix of the code word for I. Okay, so you want something where the code word for any one of your letters it can't be a prefix of another code word. Okay, so for fixed length things, this is reasonable. So let's look at the letters A. And the code words are strings in 0, 1, because 0, 1, 0, 1, 0, 1, right? That's funny, you should laugh, but okay. Maybe, thank you. Okay, so this is our prefix-free code. We're only going to use 4 characters because that's an easier example to run through. So clearly they're all fixed length. So no one code word can be a prefix of another because it's the same length, right? It can't be a proper prefix. Okay? So fixed length code words are prefix-free. We already know about this this kind of code word. This is exactly how we do it naturally. So no code word is prefix. And now, given a string, we know how to translate it. What is this? What is a string in terms of letters? Please call me a. I should have got a cab, right? I needed a cab. Oh, I'm not wet anymore. But okay, so it's a. Did I do it wrong? Please call me a cad. Okay. Do you guys know what that means? Okay, that was a bad malapropism, if I use the word correctly. Okay, so now let's do it for another. Let's do another prefix code that's not what we know. So we're going to do something that's unfamiliar, but it's still a prefix code. So here's a prefix code. I think this is not the best. I'm having some trouble. Okay, so that's a prefix-free code. A, the code word for A is 0. B, the code word is 1, 0. So 0 is not a prefix of 1, 0, right? And the code word for C is 1, 1, 0. And neither 0 nor 1, 0 are a prefix of C, of 1, 1, 0, right? They're not, they don't form the first 2 letters. Then D is 1, 1, 1. So this is a prefix-free code as well. Okay, so this is one that's not fixed length and is prefix free. And okay, so let's decode this one. Let's see if what this one is. There's A, yeah, and there's B, right? So we could read this stream without knowing its fixed length. We could read this stream and actually reconstruct our thing. There's no separators here, right? So this is nice. We didn't need to use separators here. Okay? And we could get a non-fixed length code. Okay, so it consists of A, C, T, and G. Okay, so so now if they're all the same frequency, yeah.
So the previous example, what is the advantage of having that? Because it takes up more space.
Yeah, there's no advantage, yeah. Okay, but like in DNA, we have these 4 characters, coincidentally, right? And in fact, they have different frequencies. So for a very long DNA string, A's and G's are much more common than C's and T's. Okay? So this is in some, at least I'm claiming that, and I hope there's no biologist here to contradict me. But this is a very useful thing in general, right? So when you do gzip on your computer, they're doing it at stage n. They're doing this Huffman coding. Okay, so but I'm just giving you an example from DNA. But the point is, in English, the way it works in computer science is these Lempel-Ziv algorithms is more common words appear, and you think of those as characters. And so the fact that those are characters, and then you can somehow get things that have a very, very disparate distribution. So that like this, okay? So okay, so I'm going to try it. Okay, so the expected size of the representation. So now we're going to think about probability, and we're going to say each character has a probability of 0.4 of being an A, 0.1 of being a C, 0.2 of being a T, and 0.3 of being a G. So you have n characters, and you have this probability for it being each one of these symbols. Okay? And so, so the expected size, if you use a fixed length encoding, is each one takes 2 bits, so it's 2 times n. The size of every character is 2. Okay? So we could, let's see if we could do better than that. All right, this is annoying. Maybe. Okay. Okay, so yeah, that piece of software wasn't working. Okay, so that's expected length if you use a fixed length code, 2n. So now let's use this code that we designed before, which is 0 for an A, 1, 0, 0, or not maybe the one that we did before, but one that will work. Oh, no, that one will work. Okay, that should be 1, 0, 1. That's why I want to use the other one. Okay, so let me show you something. Okay, so okay, so expected length is n. So there's n characters. Now the expected length of one character is with probability 0.4, the length is 1. With probability 0.1, it's 3. With probability 0.2, the length is 3. And with probability 0.3, the length is 2. Okay? Okay, so, oh, it's 1.9n. Okay, so with this distribution, we do a bit better by using this prefix-free code rather than using the fixed length code. Okay? Oh, yeah. Okay. Except for, you know. This is why, okay, so let me do a little bit of an aside here. I used a different viewer just because I wanted to. Oh, look at this. Oh, look at this. Oh, yeah. Oh. Oh, okay, well. Okay, so it's not perfect. Okay, is that clear? I don't know. Okay. Okay, so, okay, never mind. Okay, so, anyway, so it's midterm week and project week. We're going to goof around a little bit. So, okay. We're also going very fast in this course, so I think you guys need some time to soak up. So any prefix-free code corresponds. Let's look at it. So this is a little bit hard to understand, this prefix thing. It's like, how did I come up with this? So we're going to do another one of our favorite things is represent it as a binary tree, because as computer scientists, that's the second thing one taunts one with. Binary tree, okay? So any prefix-free code corresponds to a full binary tree. And what a full binary tree means is each internal node has 2 children. Okay? So something like this. Okay? So it's not a complete binary tree. It's not balanced. That's not what we're saying. What we're saying is that each internal node has 2 children. So the root has 2 children. The right child here has 2 children. This left child has 2 children. And the leaves are leaves. Okay, so do people understand what this is? Do people see how you might make a prefix-free code out of this? Yeah, so binary trees are binary, okay? So they have 2 ways to go. And 0 and 1, those things happen to be 2 ways too. So you just map the left branch to the 0 and the right branch to the 1. And so, okay, so the code for A is 0. The code for G is go right, right, that's 1. The code for C is right, left, yeah. There's my 1. Okay, so I could switch back to the other viewer, but I'm not going to do that. Okay, so this is really good, right? So 1, 0, yeah. 1, 0, 1. I wish I was a little taller. 0 and 1, 1. Okay? Does people understand? Okay. Okay, so this binary tree is a nice way to work with things. Now we get a better picture of how we might do stuff. Yeah. Yeah. In some sense, if the leaf is at the, yeah, so this is really good. Let's think about this. If the character, what are the leaves? The leaves are the symbols. The leaves are the symbols that you're trying to write the code for. So the symbols are A, C, T, and G. Okay, so you got a complete binary, you got a full binary tree whose leaves are the symbols. Okay, so now from a binary tree, you could read off a code word. If you go right, you put a 0. If you go left, you put a 1. And so when you get to a leaf corresponds to a path in the binary tree from the root. And the labeling on that path, left or right, gives you the binary string. Is that clear? Okay, so that's a way to map a tree into a set of code words for the symbols at the leaves. Okay? And here, A, the path from the root was of length 1. And the length of the code word was 1. Okay, and the path from the root for C, the path for the root for T was of length 3, and the code word is of length 3. And the path from the root to G is of length 2, and the code word is of length 2. Okay? So the depth of the leaf in the tree is the length of the code word for that symbol. Okay? So the depth corresponds to length. Okay? So what do I do now? Okay. Okay, so, okay, given symbols F1 through Fn, find the best prefix code. We want to find the one that okay, so now we're given frequencies, right? That's what we were given before. For ACTG, we had A was 0.4, C was 0.1, T was point something, and G was the rest. Okay? So we would have got 4 numbers for our symbols, right? Okay, so we want to find the smallest average length. We want to assign each one a code word or build a binary tree for these 4 or these n symbols, a full binary tree, that minimizes the average length of a code word. okay, where you pick a symbol with the probabilities shown here, with the frequency shown here, and then you multiply by that length, okay? So the cost of the prefix tree is the sum. Now remember, the depth of the symbol in the tree was equal to the length of the code word. So if we have character I, the length of the code word that we're going to have to put down is the depth in the tree. So it's f of I. So the probability you choose that symbol is f sub I, and the cost of choosing that symbol is the depth in the tree, right, which is equal to the length of the code word. So it's f of I times the length of the code word. So you sum over all these frequencies. And that gives you the expected length of each character, the average length of each character, okay? This is what the bread and butter of CS70 about week 5, okay? So we just say it's linearity of expectation, and this is the average cost of each character, average length of each character, okay? So now this is a function just on the binary tree. So now our notion is we're building a full binary tree, where what we want to do is we want to make the popular characters be shallow, like in high school, right? The popular characters are shallow? I don't know. Is that true? I liked it. Okay, so I just made it up. Okay, so I don't even think it's, whatever. Okay, so here's an example. So we have 4, the way we're representing the input here is that you may just write it as 0.4, 0.1, 0.2, 0.3. The name of the character is sort of kind of irrelevant. It's just something you use in the coding later. But for the algorithm, you really just need the frequencies, right? Okay, so these are the frequencies. So let's look at a tree here. Okay, let's look at our tree. So again, we see it as our tree. So A, what's the depth of A? 1. So it's 0.4 times 1. The depth of I guess G is 2. So we multiply 0.3 times 2, right? The f sub I is 0.3, and the depth is 2. I just want to get you through this notation. It's not, the notation always makes people sort of not pay attention. So I'm just trying to show you a picture. Okay, so 0.1 times 3, that's the C here, times 3. And 0.2 times 3 is that. And it's the cost we had before. So 1.9, on average, the cost of a character is 1.9. To output the character is 1.9, yeah. No. Like for a fixed length code, you could draw the full. He asked if on every level for a prefix free tree, every level has at least one leaf. But the A, C, T, G. This is a perfectly legitimate prefix free code, and there's no leaves here. Yeah, it's the most efficient if your frequencies are 0.5, 0.25. 0.25, 0.25, 0.25. For this set of frequencies, it is the most efficient. So that's what he was saying. It's like usually, if all the characters are equally likely, this is not an interesting problem. The complete binary tree is the right one. The fixed length code is optimal if you have, if all the characters are. He thinks very fast, this gentleman here. So he knew that. He's like, what? What are you doing? Why are you wasting our time? So he's on this Facebook, so he doesn't really hear me. But okay, so another view of the cost. So we're going to work with this tree. When we do algorithms, this is what you do. You play with it. You play with it one way, and then you look at it another way, and then you look at it another way, right? So we're going to look at it. We're going to say this is another way of looking at these prefix encoding, right? And so we looked at it as a tree, and we sort of said, oh, look at the depth of these trees are what we want to build a tree where the leaves are sort of the least popular, right? Okay, so Okay, so another way, so now we're going to look at it another way. Okay, so now we're going to say another view of the costs is you sum over all the nodes except the root of their frequency. So for A, the frequency is 0.4 for that node. For C, that's a node in the tree, the frequency is 0.1. For T, the frequency is 0.2. What's the frequency for this node in the middle here? No. Okay. So what's the frequency for that? What do you think should be this here? Yeah, what do you think a natural definition? One natural definition, I think that's reasonable, is 0. What's another natural definition? Yeah, the sum of the children, it's 0.3. Okay? Okay, so now we're going to sum over all the nodes except the root, which is, we have this leaf, we have C, we have T, we have 0.3 for that node. That's what the frequency of that node is. That node represents C or T. That's sort of a reasonable interpretation of this node, right? So it's either C or T. And what about this node up here? Yeah, it's C or T or G, right? Any of those characters. Okay, so what should this add up to? The cost of the tree, it should add up to the same cost of the tree as before. I'm saying this is another way to view this cost, right? So what was the cost before of this tree? It was 1.9. So there's a drum roll. Yes. Okay, it's 1.9. Okay? Does that make sense? So this way of writing down the cost is just another way to do it. Does that make sense? Okay, so, and why does this work? In some sense, this guy, 0.1, in the other way of writing the cost, it was 0.1 times 3. Now this 0.1 appears here, and it appears in the 0.3, and it appears in the 0.6. So it appears 3 times in this sum. So it appears in this sum sort of in a disguised fashion 3 times. Okay? Okay, so that's another way to view the cost. And now we have now we really kind of understand what's happening in this problem in several different ways. We have intuition about various things. So now we're going to try to do the obvious thing. Now it's only obvious after we actually thought about it for a while. So this whole class, this whole chapter is about greedy algorithms. And greedy means, oh, let's just do the obvious thing. So it's all funny, right? But sometimes it takes a while to see what the obvious thing is, what the right thing is here. Okay, so what is the right thing? So we're going to do recursion. So we have this recursion notion that internal nodes have a frequency. Okay? So once you have internal nodes that have a frequency, you can think of those internal nodes as characters again, as a subproblem. Okay? So what we start out with is we start out with a bunch of characters. And now we want to build up the tree from the leaves. Okay, so right now we start with the leaves. And now what's the first thing you want to do to build up from the leaves? I'm going to put 2 of them together. Right? If you're building up the tree, you need to know the edges to the leaves, and the edges of the leaves just tell you which ones to put together. Okay? So now which ones should you put together? Which ones should be sort of at the bottom of your tree? The least popular ones, right? So at this point it becomes obvious, right? In the first way of viewing cost, who should be deepest in the tree? You want to build up from the bottom levels. Who should be deepest in the tree? The least popular, right? The least popular people should be the deepest in the tree. So you pair them up. Once you pair them up, you have another kind of character. And that character, the frequency of that is the sum of the 2 lower ones, right? That's this other way of viewing the tree. That's where the other cost is coming in, is that you can use recursion. Okay, so it's the same problem. You're not multiplying by the depth anymore because that's a complicated global object. Here you're just adding up the frequencies throughout the tree, where these middle characters, where this you can think of this node 0.3 as a super character of C and T, and then start the problem over again with this sort of combined character CT, and just continue to recurse. And then pair up the least popular, and then pair up the least popular, and pair up the least popular. Eventually, you'll get one tree. Okay? Okay, let's see. Okay, so let's do that. So cost of prefix tree width is this depth. So this is what it says. It says you might as well, from this view of the cost, you want to make this fi, these small numbers fi should multiply big numbers here. So the deepest guys, you should pair up the two lowest frequency characters. Okay, so lowest frequency. So what are the lowest frequency characters in here? C and T, so we'll pair them up. And now we get the super character, right, which is 0.3, still not so super, right? So then we pair those up. We pair up CT and G, which is 0.3, and then we add up their frequencies, and we get a 0.6. So now we have the super character, and then we finish. And of course, this representation is actually just a representation of a tree, right? It's a sort of a, if you look at this thing, it's kind of a tree. Okay, so we can look at it, make each symbol into a single node tree. So this is the way you think of it as a data structure problem. You have all your symbols, make them into a single node tree. Now your notion is you're just merging trees, right? You pair up the least popular. While there's more than one tree, you merge the two lowest frequency tree into a new tree. That's the algorithm. It's pretty simple, right? It is very greedy. You take your characters, you merge up the cheapest ones, and then you continue. Okay? So we can see it as we can see the same algorithm. It's just another illustration of the same algorithm. We take the two ones that we think of them all as individual trees. We join them up as a tree. We join those two up as a tree, and we build our final tree. Okay? So, you know, there's some implementation details on how to do this fast. You can do it in linear time if you use a priority queue to get the lowest frequency trees, right? So, okay, so now let's think about correctness again. So this minimum spanning tree, which again is a greedy algorithm, it added an edge in a tree at every point. And what you have to make sure of when you do this is you don't add an edge that's not in a minimum spanning tree, right? It was very important that some MST must contain that edge that you added, okay? So in this Huffman coding problem, an optimal tree has a subtree with the low frequency symbols. And it should have an optimal tree on the rest. That's what we're arguing. That's what we're claiming. That's a property we need to show. For an MST, they need to show that, well, if you add the cheapest edge that doesn't create a cycle, that edge is in some minimum spanning tree. What we need to show here is we have an algorithm. We merge these low frequency nodes. We merge them. They're in there. That's part of our solution. We need to make sure we didn't screw it up. Okay? So we need to know that we have a subtree with these low frequency symbols merged. Okay? There must be some optimal tree like that. So the second part, you should also do an optimal tree on the rest of the characters once you merge the tree. That's obvious. If these two are together, you might as well do the rest as good as possible. Right? So that's what the algorithm does. It just sort of inductively says, I build everything else well. So the key to correctness, like it was in the MST, is that the edge I add at this time is right, or the pair that I merged at this time is okay. It's going to lead to a good solution. Okay, and that's basically obvious in this case. So you consider an optimal tree. You consider the deepest two symbols in there. Now, if they're not the lowest frequency symbols, switching them improves the tree, right? Because you can take these two low symbols, and now the lowest symbol, if it's higher, you just switch it. And therefore, now you've taken something that was deep in the tree, and you've made that's higher than something that's shallower in the tree. So if you switch them, you're multiplying you're improving the cost. Okay? So it's it's one of these very simple algorithms once it's all set up right. Okay. Okay. So now let's give you a break. No.
acceptable language.
Yeah, even this. Yeah. Yeah, it's not easy to see. It's actually very hard to come up with a four character example that does that.
I see. And my other question was along the lines of,
So this lemple ziv does something very different. It builds millions of characters.
what is it called?
Lemple ziv.
Lemple
You know
ziv?
when you compress on your computer?
Yeah.
So it does something like this. It takes your text and
Okay.
it makes a huge dictionary
I see.
of everything it sees.
Okay.
And now the dictionary has a bunch of entries. And some of those entries are very common.
Yeah.
Like the word the. It's in there very common.
So it's gonna encode the word and not necessarily just the character.
So now there's a hash table,
Mm-hmm.
and then the index into the hash table is what is a character.
I see.
You know, all the things you put in the hash table. Now there's some things that are only in the hash table once. So you can use a very long string to encode those.
Mm-hmm.
Right. And so that's yeah, so it's really useful.
And what's it called?
Lemple ziv.
Lemple ziv. Okay.
Yeah.
My other question was along the lines of, when we're talking about an MST, we're referring to a graph because an MST is always a subset of a graph. So in this case, is there kind of an intuitive understanding of what's our graph?
No, there's not. The analogy is just a process.
Oh, it's an analogy. We're not really doing an MST. I see.
Or not at all. It's just an analogy. In the MST algorithm, the style of analysis was to say, okay, I put this edge in.
Pick the shortest one.
Yeah, and then I know it's in the tree. So the analogy here is I'm putting these things together, and I know this is in my final information, my final output.
Do we know what we were doing? We know that there is a unique tree, or there's not necessarily a unique optimal tree. We don't know.
The frequency tree.
That's pretty complicated stuff.
Okay. There's never, in MST there's not. Yeah, this one is really, in MST you can say when there is a unique.
Yeah.
But here, like I said, all these numbers, right? A lot of numbers really make it easy.
I see. Okay, thank you.
Another question. If your frequencies were like 24, 26, 23, and 27,
Yeah, so you
could-
would get this kind of tree.
you would get,
You would get this tree in this algorithm, right?
but then is that like not? Then we couldn't have like the.
Yeah. He's asking the same question. Usually for 4 characters, this is the best tree. So they usually do this for lots of characters. Like what they'll do is I'll do it here. I'll say what it is.
And it's like if you have a lot of characters, the odds that they're all even is like very low.
Well, I mean, so what happens is in English, right? B is a very common word. So you may want to encode that with very few bits. So what they do is instead of encoding characters, they encode words. And now when you have words, some words are very common, some words are not. And now the tree is deep, right? It's like 100,000. So they run up encoding on 100,000. So this is like a really used algorithm. It's used every day in your browser. It's used like when you download a web page, it's compressed in this way. So yeah, I can. Okay. So let me point out. So several people noticed that this is the optimal tree for almost any set of frequencies you pick for 4 characters. Okay, so they're like, how useful could it be? So the point is, there's this big. Do you guys surf the web? Okay, yeah. So when you surf the web, half the time, depending on the particular web server and your browser, the file is sent to you compressed, even if it's not an image. It's just sent, that HTML is compressed by the server and it's uncompressed by your browser. And it's compressed, it's not compressing each character. The characters may be English characters. It's not thinking of the characters as A, B, C, D, E, F, G up to whatever your normal alphabet is. What it does is something called the Lemple ziv algorithm, which intuitively takes all the English words and puts them in a dictionary. Okay? So now you have this huge dictionary with 100,000 words in it. But then you think of all those words as symbols. So this algorithm being efficient is very important. This, the fact that you need to do this in linear time. It's very important. You're doing it every, all the time on the web. What you're doing is you have a huge dictionary of words in your document, and the characters are which is again a hash table, because it's an index into this table. And that index is a symbol. So you have index 1 up to n. Now, the index that points to the word the is much, that word the is going to appear in your document much, much, much more than the word, elephant. Right? So you want to use many fewer, the word blah, okay? BLA. Right? Those are the same length, but you want to use much fewer characters to represent the than you do to represent, blah. Okay? So this algorithm is really an important one that you're running basically all the time. So this example on 4 characters, it's very hard to actually come up with a 4-character example where this is not the optimal solution. Okay? But for hundreds of thousands, for what you're doing, it's remarkably effective. Okay? Okay. Okay, so this is, somebody else asked a question. We're not building an MST in a tree, it's just an analogy. It just says, when you design greedy algorithms like MST or Huffman coding, we do something, we make a decision, and we can't go back on the decision, and we have to argue that decision was correct. Okay, so that's the analogy here. We made the correct decision to merge these 2 characters, to get the unpopular people together. Okay? Has all kinds of implications for high school. But okay, so now let's think about another application. This is also from the web. So you have your web server. You read your response from the wire. Okay, so this is a dangerous thing to do on your computer when you read a response from the wire, because somebody else is injecting data into your program. Okay? So, for example, you don't want to read that response and then run it as a program. Like in Scheme, they say it's a so you have to be a little careful. So maybe at some point, that's fine. So you have to be careful what you do with A. You can't execute A as a program. Or you can, but you might have severe consequences if you do so. But then maybe you go and you take B and you concatenate A with C. That's what, it's a polymorphic, fancy language, right? So we're doing that. And at some point, we issue an SQL command for B. So what this does is it allows somebody on the web to inject something into my SQL database. Okay, so this is dangerous. This is considered dangerous. And this is something you want to analyze. And this is just program text. You want to analyze your program text for dangerous things like this. So A is input from the web. So A, we're going to call it tainted. Because we know when we read a response from the web that we have no control of what's in that data variable. None, right? Anything can be typed at all. Okay, so if A is tainted, B is tainted. Okay, so my coloring is a little bit off, but that's what this statement says. So I'm translating the statement line by line into logical statements. I just look at the statement A, and then I write down the statement A is tainted. Then I scan through the program. And then I see this statement, B equals A plus C. And I said, oh, A is if I don't know whether A is tainted or not, but I can just write down the statement, if A is tainted, B is tainted. I can also write down the statement, if C is tainted, B is tainted, right? I only need to look at that. I only need to look at that one expression and say, oh, look, B is a function of A and C. So if either A or C are tainted, then B is tainted. Okay? And then finally, this third one, D is equal to SQL command of B. That's sort of the statement, oh, okay, just from that local statement I can say, okay, well, B should not be tainted because look, I'm sending it to an SQL thing. Okay, so I can write down all these statements in logic. I'm going to write down the statement A is to A as A is tainted, B as B is tainted. I'm going to say the first statement here, A implies HTTP read response, says that's the way we express it is we say, oh, A is true. Nothing implies A, which means A is true. True implies A. So the second statement, if A is tainted, B is tainted, well, that says A is tainted implies that B is tainted. And the third statement is B should not be tainted is not B. So these are statements we can output about our program. We can say, well, we know that if A is tainted, we know that if A is tainted, B is tainted, we know that if C is tainted, B is tainted, and we don't want B to be tainted. So just a linear time pass over your program, you can write these logical statements. So the question is, you want to answer, do all these statements hold? Can we satisfy them? Can we get the condition that B is not tainted? And in this case, obviously not, because A is tainted. A is tainted. A implies that B is tainted, and we want not B, but we got B. Okay? So in general, we want to be able to do this analysis. This is called taint analysis. Okay? So here's another way to express it, is another set of formulas. You know, x1 and x2. If both of these things are true, then x4 is true. So it's kind of the same. And these are things you can derive from a program locally. You just look at the program and say, oh, okay, well, if these two things hold, then this must also hold. Okay? So, so what we want to do is, in some sense, in the taint analysis case, what we want to do is make sure certain things don't happen. Okay? These things that are happening are bad, right? Tainting is happening. So we want to make things that don't happen. So we want to find a consistent assignment with the fewest true variables. Okay, so here I kind of express this as a different thing. I want to say I have implications and I have negations of things. So these are the things I get. So these implications, I don't care much about implications. I can just set everything to true and all implications are true. But if I have a not somewhere, then that's a problem. Okay? So what I want to do is just avoid these bad things. And the way I can do that is find a consistent assignment with the fewest number of true variables. Okay? Okay, so the reasoning. Let's just go through this one. So I want to find an assignment here with as few as possible true variables. So what's true right now? What do I have to set to true in this set of clauses? Yeah, this notation implies x1. Nothing implies x1 means x1 is true. That's just the way we represent it. Okay? So x1 must be true. And then what happens? x3, we have this clause up here where x1 implies x3, so x3 must be true. So x2 must be true, and x4 must be true. And now we're done. Nothing else has to be true, right? X5 doesn't have to, x2 and x6, the only thing that that can make x5 have to be true is x2 and x6, right? And x6 is not true. The only thing that can make x6 is true is nothing. Nothing's making x6 be true. Okay, so this is one satisfying set of assignments here. Okay, for these kinds of clauses, right, all true is a set of satisfying assignments. Okay, so in some sense, what we're trying to do is just find a consistent assignment with the fewest number of true variables. Okay, that's sort of one way of phrasing a horn satisfying assignment. So those are true. But you could also set x5 to be true or x5 and x6 to be true, and this set of inequalities are the set of implications satisfied. But if we start throwing in negations, we generally want to avoid true things. So you could have an interpretation of this. If x1 is cold-blooded, x2 has scales, x4 is reptiles, x3 is snake. So if x1 and x2, if it's cold-blooded and it has scales, it's a reptile, right? That's a way to interpret this logic, right? This is stuff you should have seen. So, so Hornstadt is exactly this. You write down these variables, and you also throw in some clauses saying, you know, not x1 or not x2 or not x3. So that things generally you want them to be false. These are sort of bad things to happen for the application of tainting. I don't know that it's bad that something's a reptile, but that's a different statement. Okay. So so the algorithm, what is the algorithm? So we want to set as few things to true as possible. So this suggests a greedy algorithm. Even asking the question this way suggests a greedy algorithm. So what's the greedy algorithm? Well, you set a variable as true if you have to. That's it. Right? So property, any variable set to true must be true in any satisfying assignment. Right? So that's the property we need to say this algorithm works. Okay? And it's basically by induction, right? The first k that are set to be true, they have to be true, right? That's what we assumed by induction. And then when we set one to true, we look at it. We're looking at our formula, and we see an AND clause with a x1 and x3 implies x4. We know that x3 has to be true. We know that x1 has to be true if they are true. We're assuming they're true. Okay, this is currently set to true, and this is currently set to true. So we assume this is true. So these have to be true in any satisfying assignment. So then this has to be true. Okay? So it just follows. It follows easily. This is a kind of an easy property, but it's pretty powerful. Okay? So now if you have clauses of different form, it's not necessarily, you don't really get much out of them. Right? If you have x1 or x2 implies x4, you kind of get stuck a little bit, right? Or if you have a not, yeah, you know, either this one can be true or that one. You know, knowing that both of these are true doesn't, yeah, it does tell you that you have to do something, right? But both of these being true doesn't really tell you anything about x4. Okay, so you don't have this sort of monotonicity. It's very important that you don't have negations here in the implication, because then false would imply something. Here, in all of these negations, the only decision is if it's true, then something happens. If it's false, so far you don't have to do anything. There's no propagation of anything. Okay, so Horn technically also has these negative clauses. So negative clauses are fine. It says, if you throw in negative clauses, how do you know the previous solution was fine? The previous solution is fine because everything that's true has to be true. So the negative clauses, you know, if they cause you a problem, it's because they have to. You know, we could just ignore the negative clauses in the Horn formula when we're solving it. Okay. So if a negative clause is false, it must be. Okay, so now you want to do an efficient implementation, right? So what was the algorithm again? You set x1 to be true, right? And then what did you need to find? You need to see who depended on x1, right? So those are called antecedents, the things on the left-hand side. You need to see who has x1 on the left-hand side, and then you need to see, oh, look, x1 is true, and this x1 implies 3. You had to find that particular clause. So you just build a data structure that tells you which clauses you're in. And then when you need to keep track of the count of the true antecedents, and when there's enough, for example, this x5 and x1 implies x3, or the x1 and x2 implies x4. Once you see that x1 is true, that means one of your antecedents is true. Once you see that x4 is true, that means x2 is true, that means 2 of your antecedents are true, which means you must be true. Okay? So all you need to do to tell whether for each clause to tell whether you need to do something, you need to count the number of inputs that are true. Okay, so the data structure is you connect each variable to the clauses with that variable as its antecedent. And that you can do this in linear time too. Okay, so any stat formula. Yeah, x1 being true doesn't mean anything about x2 or x3, so it doesn't help you. You can't progress here. So this particular algorithm fails for any stat formula. Okay? Okay, so now we're going to talk about a third problem. Maybe I'll just describe it. Maybe we'll go over the analysis next time. We'll see where we get. Okay, so the input here is a set of items. Let's just call them 1 through n. Okay? So we have an input of just a set of items. And then we have a set of sets which are subsets of these items. Okay, so again, this is that notation which makes people not pay attention, but we'll get to some examples in a moment. So we want to find the fewest numbers of sets that cover the set of items. Okay, so it's a little abstract. So let me point out an example. So the set of items can be users, and the set of sets can be, it could be cell phone users or places where you want to serve cell phones. And the possible, this is not the best example because users move, but let's say they don't move, okay? They're houses. So the possible cell phone tower locations. Now from some location you can cover, on campus, you can cover, Valley Life Science and genetic plant biology, and another location and people around there, right? In another tower over on Evans, you can cover things over on the uphill side of the campus, right? So each cell phone, each location covers some number of possible users, okay? And now you want to buy cell phone towers. You want to place your cell phone towers so that you cover, say, all of campus, okay? With cell phone coverage. Or, this is what we wanted to do for Air Bears. Right? You want to put up your Air Bears repeaters to cover all of campus. And the users will be the rooms. Okay? So the set corresponds to, locations, really. This location covers these 5 rooms. This location covers those 5 rooms. And then all the rooms are your set B. Okay? Does that make sense? So this is it's a reasonable problem. You do want to minimize the number of repeaters you want to put out there, right, to cover everything well. Okay, so each cell phone tower possibly covers some users. That's this subset of the rooms or subset of the users they cover. Another thing is customers, and you want to say everybody should be within a certain distance of a Walmart, right, because that's very important. And so the sets are locations for Walmart. So Walmart wants to cover everybody, wants to make sure they're all within a certain distance of Walmart. Okay? So you want to minimize the number of locations you have so that everybody is covered, everybody is served. So each location corresponds to a subset of the customers that are close to it. Okay? So that's what it means. S1 may be Emeryville, and it may cover everybody in Emeryville and North Oakland and parts of Berkeley. Okay? So this is, this is a really wide job responsibilities. So you want to build a company and you need all these capabilities. And then people have, some people can do Ruby and Python, and some people, nobody can do Perl. Some people can work with Unix, right? So, well, nobody can read Perl, I guess is the thing. Okay, so you want a factory. It's really everywhere, right? So you have a factory, and the factory needs various things. It needs touch screens, chips, and of course, if you make an iPhone, you need cheap labor. And so, and who do you get it from? You get it from your suppliers. Okay, so some suppliers may be able to provide different subsets of these items. Okay, so it's pretty universal, this problem. Okay, so how might you, so do people understand? So this mathematical notation, again, is confusing But let's just pick one of these applications and come up with an algorithm, a greedy algorithm. Okay, and then it'll be the right one. Okay, in this case, the greedy algorithm is really very apparent. So, say I have this. I have a list of let's do customers and Walmart users. Okay, Walmart locations. So I have a set of customers and I set up locations where I can put up my Walmart. Which one should I pick first? Yeah. Okay. The one that can serve the most customers. Does that make sense? Does that seem like the reasonable thing to do? You just put up the Walmart where you have the most customers. It's an algorithm. You're not actually putting it up. You're just going to run this algorithm, right? So what's the next thing you do? Right. Okay, so you should be thinking yourself, what do you think? Do you all figure out what to do? So you remove everybody you covered, and then you pick the Walmart that covers the most remaining customers, right? So the algorithm here is very natural. It's exactly what you think you should do. So how well do you do? So I'm covering the most possible that I can from any of the remaining possible locations. Do you think you do well or not well? You have an intuition here? Okay, so let's go on. Okay, so who thinks you do optimally? Maybe, I don't know, we can try this. Why don't you talk to your neighbor and see? I'm probably going to never get you to quiet it down again unless I tell you a bad joke. But think about it. Do you think you do optimally? All right. You can think about trying to write an example down if you want to see if you might do optimally. So, okay, so who thinks you can do optimally? This algorithm is perfect. Who thinks that? Okay, who thinks you can't do optimally? This won't do perfectly. Okay, so you're right, it won't do perfectly. That's right. So now come up with an example where you don't do perfectly. Why don't you try that for a minute or two? No, I'm going to try to come up with an example now that I asked you to. But let's see. Okay. Okay, so does anybody have an example? Who has an example? Okay, so good. How many people think you are really convinced you can't do optimally? Okay. Okay, so here's an example. This one has a set cover of size 2, right? These are the items, and these are the sets. Right, so this is the optimal set cover. It has a set cover of size 2. Okay, so then what I'm going to do is I'm going to throw in another set that has this, it's a deceiver set. So it has these 4 items in it. Okay? So the first thing you're going to choose is you're going to choose this set that covers these 4 items. Maybe I should draw it more geometrically to see, yeah, so I'll draw it this way. Let's actually deal with cell phone towers, okay? So my cell phone towers can be here, or here, or here, okay? So now these 2 cell phone towers, this one covers this one covers this one. And that would be the optimal solution. Those 2 cell phone towers cover everybody. But then the circle one covers these 4, right? So this algorithm would say, oh, I'd be greedy, and I'd pick this one first, because that one covers 4 of my sets. But then to get this guy and this guy, I need to pick these 2 anyway, right? So I'd have to pick 3. Okay, so it's not a perfect algorithm, this greedy algorithm here. But we're going to show it's pretty good. Okay, so I think, but let me show you the algorithm, and then I'll defer the analysis to next time. So this is what we said. We remove all the elements from S. In this case, there's 3 sets, right? There's S1, S2, and S3. We take S1, we remove all the elements, and then what we have is we have a new situation where you have S1, S2, which covers this one, and S3, which covers this one. Okay? And now so here, the only way to cover this to give service to this particular X here is S2, and the only one here is S3. Okay, so this took a cost of 3. And the optimal was 2. Okay? Okay, so this is the algorithm, and this is why it doesn't work. Okay, so and I'm going to defer the analysis to next week. Oh.